That's a good place to start. I didn't record that, but oh, that's not us. That's not us here. Let's see here. All right. A little bit of administrative work. We are going to start chapter 3 today because we finished chapter 2 last day. And because we're starting a new chapter, I'm not going to do any review, and it was just this week, and we're not relying on it, so you'll have to review on your own. But I did make a note here so that I can talk about it. I posted a lot of assignments. At first, I thought, oh, I can just kind of condense these into just 2 big assignments, and I could have done that. But the reason I kept them as little bitties is because then if you miss one, it's not a big deal, right? And they're just going to spread out your grade over more things. Same questions that I would have just zipped into one. So it's better, I think it's better if I just keep them all little. And if you don't like that, you can just pretend they're all one big assignment and do it that way. But your grade is still going to be split. Okay. I'm going to change it to be one of you. Okay, we're done with week 1. Week 2 was last week. We're in week 3, so this is what I mean. Posted a lot of assignments. I posted Excel assignments as well, where we kind of get started working with Excel. Now, I made all the Excel assignments and also the probability assignments. They're all due. Sorry, I don't have a pointer on here. That's why. They're all due on the 30th. Okay, and so you've got quite a bit of time to work on them because there are so many. And the Excel assignments, I'll typically give you a little bit more time to work on them, right? Because you might need to come see me for help. That's okay. Or Kate, yeah.
Did you say all of these assignments are due on the 30th?
Some of them are due earlier. Rude, right? I think assignment 2 and 3, which is what we finished last day. So summarizing numerical data and summarizing categorical data. Let's see here. Is due on Thursday, the 26th. Okay. Because I need you to stay on top of those things. The Excel ones and the probability ones that we'll be able to do after today, they're due on the 30th. There used to be a nice calendar. How do I get to our calendar? There's got to be one. I know on here it shows up with all my due dates because I put them in, but some of these are not our course, obviously. These are just all my courses, so they should show up there at least. But there used to be like a nice calendar, but I don't know where it is. I got rid of it. Maybe. So like I said, I could have zipped these up, but I didn't, and that's okay. So can pick away at those. We'll be able to do, we'll see how far we get into probability. So chapter 3 today, right? We'll be able to do assignment 4 for sure, but assignment 5, maybe not quite yet. We'll see. I'll let you know at the end of class. Okay. Any other questions? No. All right. So probability is I'll say not my favorite thing. And unfortunately, that usually tends to make it not your favorite thing. Oh. Wait. Let's see. Is that okay? Maybe it's set to not mute people as they come in. I gotta fix that. Anyways, so probability, not my favorite thing. But once we're done with chapter 3, we'll kind of use these concepts, but in a different way. And so we don't need to think about it too much after chapter 3. And so it's kind of a necessary hurdle. And then once we're through it, then we're kind of on to some fun stuff. So probability. Well, let's start with what we said last day. So what we said last day was that probability is the same thing as a proportion, which you can multiply by 100 and get to a percentage. I am reluctant to use an equal sign, but I'll use an approximately equal a percentage. We know that relationship and how that works. What's key here is that all these 3 P's mean the same thing. Probabilities, proportion, percentages. We need to be able to move fluently between these 3 things. Okay? And we can use them interchangeably. Okay. All 3 can be used interchangeably. There's a lot of that in stats. So I really like that Kate likes probability. That means she's more of a math person than me. No. But so she'll enjoy this stuff. All right. Today, just introducing a lot of terminology again that we'll be able to apply and solve problems later on. But first, we just need to talk about just as the section's called defining probability. So just defining all these things, all these concepts. And we start with a random process. And so a random process is just any situation or process where we know what outcomes could happen, right? But we don't know which particular outcome will happen. Okay? And so I'll highlight this here because we're going to be talking about a random process quite a bit. Okay? So some examples. Cute iTunes. Anyways, coin tosses, right? If I tell you, oh, I'm going to toss a coin, you know that the possible outcomes are heads or tails, right? We ignore the very rare instance where it lands on the edge. That can happen, but the probability is very low, and so we ignore it. You can roll a die, right? Probability is going to talk a lot about kind of coin tosses, rolling a die, drawing a card from a deck of cards, right? That kind of thing. And so if you're into kind of game theory, then this one's for you. We will sometimes say that a process is random, even though it's not truly random, but that's okay. So what is a probability? A probability, there are 2 possible interpretations of probability. Now, for us in this course, we are frequentists, but I do want to mention the Bayesian interpretation as well. But before we can do that, if we have a probability that we want to talk about, usually we use the probability notation. So P of A, whenever we see these brackets here, we're going to read it as of, so P of A. The probability of event A, right? Calling A just a general name for the event. Now, the first fact that we're given is that P of A has to be between 0 and 1, okay? So probabilities have to be between 0 and 1, making them proportions, right? And so probabilities must be between 0 and 1. That's our first rule, right? So generally, the definition is that P of A has to be between 0 and 1. Fine. Okay. So like I said, we're going to take the frequentist interpretation, which is also how I was raised, and I mean academically raised. I'm a frequentist, which says that the probability of an outcome is the proportion of times the outcome would occur. So would occur if we observe the random process an infinite number of times. Okay, that's obviously hard to do / impossible. But that's the idea, right? So the reason that we say, okay, the probability of flipping heads is 0.5, right? Then what's that really saying? If I flipped a coin an infinite number of times, I would expect to see heads 0.5 or 50% of the time, right? And so that's how we define probabilities, okay? But we don't need to observe this random process an infinite number of times. Usually we can just assume that, okay, if I have 2 outcomes and only one of them has to happen, the probability is 1/2, right? The Bayesian interpretation is for some event, so I might think that, okay, the probability is 0.3 to flip a heads. And you might say, well, I think it's 0.7. And then we just kind of take that and correct our guesses until we land on something. It's weird. It is kind of the new age of statistics. And so we're kind of moving in that direction because we have computers now, and that was really hard before. But for us, we're still using the frequentist interpretation. So that's the only thing that you kind of, well, you don't even need to know that. So which of these events would you be most surprised by? Exactly 3 heads in 10 flips. Surprising, but okay, reasonable. Exactly, so notice here, we've got the word exactly. So exactly 3 heads in 100 coin flips. Okay, that's even more surprising than in 10. Fine. But of course, 3 heads in 1,000 coin flips. Now that is surprising, right? Yeah. It can happen, but it's unlikely, or the probability is very, very small, right? And so let's see here. I think there was something I wanted to add here. It's not coming to me. That's come to me later. So the law of large numbers says that as you observe more and more outcomes of this event, right? So as you flip the coin and you're starting to accumulate these observations, then the proportion, which remember is also going to turn into the probability, right? The proportion of a particular outcome, let's say flipping heads, right? Which we're going to denote by p hat of n. Now p hat is a sample proportion. And we have p hat subscript n, which is the sample proportion after n outcomes. Or n, it's the sample proportion after, after n observations. So what happens is that, okay, as you collect more and more observations, right? So as your n increases, then your p hat will stabilize. So your sample proportion of successes is what we're going to talk about. So flipping heads, for example, is going to stabilize at this population proportion. We're going to come back to p and p hat quite a bit. So it's good to establish them here. The population parameters, right? We usually denote them by Greek letters, right? We had mu, we had sigma squared. So this is the only case where we don't use pi, but we could use pi or p if you'd like. Okay? It's just that pi is also a number, and so then it gets kind of messy, and so that's why we just use the p. But I'll know what you mean. If you like to use pi and keep them all Greek, it's fine by me. All right. So what does this look like? A visual representation of what our kind of gut reactions were here, right? As I increase my n, right, then I'm expecting the number of heads to be about 50% of the time, right? And so what happens is if we have our n, right, and we have our p hat of n, might start here, and we kind of have this big activity, but eventually it'll stabilize at what number? 0.5 if the event is flipping a coin and observing a head or heads. Which is it? Heads? It's only one head. Anyways. So we're okay with this fluctuation here, but after some sample size or some number of observations, we do expect it, and it does stabilize around the population proportion, which is going to be 0.5. Okay. When we're talking about outcomes right? So then we usually use, or I usually use these kind of slots to indicate what the outcome was, okay? And then I can replace these with the probability of those things, okay? And so if you're tossing a fair coin, if heads comes up on each of the first 10 tosses, so here I've got 10 slots, blah, 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 then, or yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we're talking about the 11th slot. What's the probability or the chance that another head will come up on the next toss? Kind of a trick question, I guess. You want to say it's something kind of less than 0.5 or more than 0.5, but it's not, right? Why? Because the coin doesn't actually care what it did in the past. And so we say that these coin tosses are independent events. So that's going to be an important concept because we usually, and it's called the gambler's fallacy, right? Or the law of averages if you want, but the law of large numbers says that, okay, it doesn't compensate, right? So, okay, you had this rare sequence, sure, but the probability of having another heads or tails is going to be the same as before, right? So it doesn't matter. And so the probability of H, so how we read this probability notation is the probability of H on the 11th toss is still the same as the probability of a tails on the 11th toss, which is still going to be 0.5. And so the coin, because it's an independent event, is not due for a tail, even though that's usually what we want to believe. Okay. You've probably heard the term mutually exclusive or potentially even disjoint, just kind of in regular language. Okay. They mean the same thing. So another one to link up. There's a lot of linkages in all these terminologies, right? But you can use whichever one you'd like, as long as you're able to read. If I say, oh, these two things are mutually exclusive, then you can understand that to mean disjoint and vice versa. What does that mean? Outcomes that cannot happen at the same time. Okay? For example, right, if I flip a coin, then it's either heads or it's tails, and it can't be both at the same time. Okay? Now, I want to start introducing, and maybe I need a little bit, I don't know, there's not a lot of space here. Start introducing Venn diagrams to illustrate these things or these concepts. So this is called a Venn diagram. And we can use these to illustrate kind of outcomes and shared spaces. And so here, we haven't introduced it yet, but I will put it on here just so it's not missing. But this is going to be called the sample space. So all possible outcomes are in this rectangle. Yeah. Now for disjoint outcomes, it would look like this, where we have heads and we have tails. heads can happen, tails can happen with some probability, 0.5 and 0.5, right? But what it looks like is there's no overlap, right? You can be in heads or you can be in tails, but you can't be in both. Okay. So some other disjoint outcomes would be you can't both fail and pass a class. It has to be one of those. A single card drawn from a deck cannot be an ace and a queen. It has to be one of those. Right? On the flip side, though, we do have non-disjoint outcomes. Okay? Kind of more elaborate. You can get an A in stats and an A in econ in the same semester. And so what does that look like? Well, in terms of a Venn diagram, non-disjoint, oops, look like this. So here we have stats and econ. And here's everything else. Okay. So an A in, I'll say A in stats and an A in econ. You can have an A in stats, but not in econ, right? Or you can have an A in econ, but not in stats, or you're allowed to have an A in both, right? And so now there's this joint space, A in both, where that's allowed to happen, right? And it can happen. Same thing if we talk about a deck of cards, right? I can draw an ace and it can also be a red card, right? There's a little bit of overlap there. Okay. So disjoint and non-disjoint outcomes are gonna, okay. What? Everything's slipping. Okay, that's okay. I'll just hold it. Because that would be a bummer. Everything went crashing. What was I saying? So for the most part, we're going to be talking about non-disjoint outcomes, and then we'll have a special case of disjoint outcomes. Okay, so for the most part, we can go ahead and assume that things are non-disjoint until we can show that they can never happen at the same time. Okay. Here is a deck of cards, and there are some key things about a deck of cards that I expect you to know. Okay, so some card facts. That sounds like hard facts. I'll put them on the previous page. Okay. Ignore those lines for now. But here is a deck of cards. That's what a deck of cards looks like. And so you're feeling like, oh, I'm a little rusty, like I usually do. Then, because I always want to call these clovers, but they are clubs. And these are spades. Thank you. Hearts, rectangles, no, diamonds. But I always want to call these clovers, and so then I clam up whenever I have to say it. But anyways, so a deck of cards, just some kind of facts that I do expect you to have a handle on, right, is the total count is 52. Yeah. There are 4 suits. I'll just do it alongside here. Clubs, spades, oh man, hearts, diamonds. Each suit has 3 face cards, which are obviously the ones with the faces on them. And each suit has 13 cards. There's already overlap that we're talking about, right? The 13 cards in the suit, but then 3 of those are face cards, right? And so there's already overlap that we can see, right? And so we're gonna need to keep track of that. What else do I expect you to know? I guess 26 black cards. Or let's just say cards in each color is 26. How can we use those numbers? If I ask you, what's the probability of drawing a face card? What would you say? The probability of a face card from the entire deck of cards, that's going to determine what the total is, right? So then I have to keep track of that 52, right? And then a face card, I have 12 of those. And so the probability of drawing a face card is going to be 12 over 52. Good. And so we're going to use those counts different ways for different probabilities. For example, now this is for next week, but what if I told you that I drew a diamond, then what's the probability of it being a face card? So you know now that, okay, it has to be one of these. So now my total isn't 52 anymore. It has to be just these 13, right? And so then I have 3 face cards out of 13, and that gives me the probability. So just as an example, say I have drawn a diamond. What is the probability it is a face card? This is what we call a conditional probability. Which is in the next section, but so we're gonna get there. Perfectly reasonable. Looks like we already know how to do it, but what we're gonna say is the probability, we want to find the probability of a face card given it is a diamond. So if I know that it's a diamond, I only have 13 of those, and the probability of a face card is 3 of those. So 3 over 13. Right. Gonna build up to that. What's the probability of drawing a jack? Oh, I guess I should have said that. Jack, queen, king, but I think that's pretty obvious. Fine. There. We'll see if anything else comes up. Oh, and these are aces, of course. We're going to use aces 1, so ace is low, because otherwise it makes our deck look weird. So now I know cards, you might not be too familiar with cards, but I do expect you to have that kind of ground knowledge, because I told you. Now, what's the probability of drawing a jack or a red card? Or, okay, we can map this out, right? We've got, okay, our jacks here. I have 4 of those. And then a red card, which they used blue for, I guess, here, is all these guys. So what could you do? You could add all those up, anything that you've kind of circled, and take it out of 52, right? Just being careful that one way or another, you don't count these little guys, the red jacks, twice, right? And so one of the ways that we're going to remedy that, right, is because it's going to be easier to talk about the probability of a jack overall and the probability of a red overall without kind of extracting the overlap. So what we're going to say is then we're going to subtract that overlap where it's a jack and a red card. Okay. And so you might have just counted 2 and then recognize that, okay, these are red, so I'm going to count them when I count the red cards, right? When we have the visual, that's easy enough to do. But when we just have probabilities given, right? The probability of A is 0.6, the probability of B is 0.3, and the probability of A and B is 0.2, then that's harder to think about. And so we're going to develop this general formula for us to use. And so fractions, no one likes fractions, but luckily they're all in the same base, right? So same denominator. We need a common denominator. Notice the common denominator. Or if you have a snazzy calculator, like these, something like this, it usually just does the fractions for you and simplifies them. And so that's nice. So then you don't have to. Probability of a jack overall, right? Ignoring that overlap for a little bit, is 4 over 52, right? The probability of a red, well, we know there's 26 reds out of 52 cards, or half of them, right? And so it's tempting to simplify these, but I wouldn't, just because you do need that common denominator. And so 26 over 52, and then the overlap, the jack and the red, that's these guys, right? So we have to subtract the overlap of 2 over 52. And I drew over there. Fractions, bad. We subtract the overlap just once, because if you think about it as kind of puzzle pieces, right? You've got your jack puzzle piece, which you've counted the probability of, and then you've got your red puzzle piece that you know the probability of. All you're doing is you're just subtracting the overlap once to kind of smooth it out, is how it works in my mind. That's hard if you're watching the video. There was like a lot of hand gesturing. There. So when we're talking about or, right, it could be one or the other. And let's just look at the Venn diagram of this in general. So I have some outcome A and B. Then this overlap is A or B, or sorry, A and B. So then if we had to shade A or B, that's going to be all that, including the overlap, but just once, right? So visually, that's what it looks like. Okay. We've got a contingency table so we have randomly sampled students who either think marijuana should be legalized or not in the rows, or they agree with their parents' political views, yes or no, or no and yes. Okay, and then we have counts. And so we've surveyed a total of 165 students. You can make a note of that first. Right, that's our total. And what we want to know is the probability that they think marijuana should be legalized. Okay, so I'm just going to highlight legalize, yes. I'm interested in those guys. Or they agree with their parents' political views. So they share their parents' politics. Yes. So what I could do here, right? There's a lot of ways that you could go about solving this problem. Yeah. But I think what I'm going to do is I'm going to talk about the probability of legalize yes is, so regardless of the politics, it's going to be 114 out of 165. And we can talk about the probability that they share, I'll just call it share politics, is 118 over 165. In those numbers, right, it's pretty obvious that I've counted that 78, the overlap, twice. And so I'm going to make a note here that I also need the legalize yes or legal yes and share politics is 78 out of 165. Right. So using the same method as before, right? I can take, okay, legalize yes, the probability of legalize yes, plus the probability that they share politics, and then subtract the overlap where they say legalize yes and they share the politics. And so this becomes the probability of legalize yes or share politics. It's going to be long. Is going to be, can I just go for it? 114 over 165 plus 118 over 165 minus 78 over 165. Making sure that you're subtracting and not adding that overlap. If you pull out that common denominator outside, then you get B. Nice. This is kind of hard to recreate, I think. So luckily, we have this general addition rule, which is going to be on our formula sheet. And I guess, is it time for me to show your formula sheet? Think you can handle it? Okay. Let's see. First, I go back to my normal role. Edit. And show our formula sheet. Uh-oh. This is why I don't give it out on the, it's only 2 pages. And we're going to be working through this nice and slow. You'll have a copy of this formula sheet. I'll bring some copies for next week. I forgot them today. Sorry about that. And so you'll have a copy for home or wherever you want to keep it. You can always have more. And then you'll have, I'll bring fresh copies for the test, but just so you know what you'll have on the test. Let's see here. I'll open this up. Can spend some time here. This is from chapter 2. All of this. And then this is chapter 3, which is what we're going to work through today and introduce some of these. And then 3.4. But we're going to work through these nice and slowly, and it won't be so bad. Yeah. So here it is. The addition rule for events A and B says that the probability of A or B is the probability of A plus the probability of B minus the overlap, which is the probability of A and B. Cool. Nice. So far, we've only seen this fact, but we'll pick away at the rest of them. So far, we've only seen these 2. Right. But we'll pick away at it, like I said. Okay. So this is on your formula sheet, and it's called the general addition rule. And for us, right now, just pay attention to the ors and the ands, right? I do want to make a note here because I can't remember if there are any assignments, but it's going to be worthwhile learning. So or the symbol for or is a capital U for union. So I try to use the words, but sometimes I kind of slip into the union kind of set notation. And the symbol for and is an upside down U. Oops. That's not very nice. Better. Which is called the intersection. One thing that I will point out is that notice if you take your upside down U, you can kind of imagine it as an A, and then it's and. The ands and the ors will play a larger part later on, where and is going to mean multiplication and or is going to mean addition. Yeah. And so or will usually mean addition, right? Even here, the probability of A or B is the probability of A plus the probability of B. And then we have to subtract the overlap. But in general, when we're using or, right, we're going to have this addition here versus and will usually mean multiplication. This looks like mean. Usually mean multiplication. Here's a fun fact. If two events are disjoint, right, then we have to search the archives. What does it mean to be disjoint? It means they can never happen at the same time. What's the probability of A and B? Must be 0, right? They can never happen at the same time. And so then we have this special case where we're subtracting 0. That's okay. So if we have disjoint outcomes, what can we do? If we want the probability of A or B, we can just add them up, and then there's no overlap to subtract. Yeah. And so this is also something we can use to determine if something is, or if two events are disjoint, right? If I tell you that the probability of them happening together is 0, then you know, then they are disjoint, right? And vice versa. And I'll just show that the probability of A and B, but this is equal to 0, so you don't have to write it out. But it's always good to start with a general addition formula. And then if the overlap is 0, then you can just put 0 in and be happy. Because you don't want to forget that overlap. Any questions so far? Okay. We're going to be given probability distributions. And so a probability distribution lists all the possible events and the probabilities that they have. Yeah. And so the probability distribution for the gender of one kid, they really talk about kids, which I find kind of jarring, one child, but kid. although it makes me think of, aren't baby goats called kids? Which is way funnier to think about. So the gender of one baby goat can be male or female, right? And so the probability is 0.5, 0.5, let's assume. So often I'll give you the probabilities in a table like this, and it's called a probability distribution. Now, there are rules for probability distributions that we need to be aware of. Okay? And so first rule is the events that you list have to be disjoint. So it's more for special cases, right? But these events have to be disjoint. Okay? The probabilities have to satisfy the overall rule of probability. Okay? And so each probability must be between 0 and 1, because any probability has to be between 0 and 1, right? And the probabilities must total 1, because this has to list all possible events. Since it must list all possible outcomes, I'll call them. So if they don't add to 1, then you either haven't listed all the possible outcomes, or there are too many and there's overlap potentially, okay, which violates the first rule. Okay? So on your assignment and on the tests, right, I'll give you a probability distribution and I'll ask you, is this a valid probability distribution? And you would say yes or no, but you would walk me through these rules, right? Yes, because each of these outcomes is disjoint, right? They're all disjoint, and each of the probabilities is between 0 and 1, and the probabilities add to 1. Right? More often, I give you a bunch of options for probability distribution, and then I ask you which one is the valid probability distribution. Okay? And so it's the one that satisfies all this criteria. If we have 2 kids, 2 baby goats, we could have a male, we could have a female, we could have a male, then a female, versus a female, then a male. Those are disjoint outcomes, right? And so the order here is telling me the order that they were born, I guess, or being considered, really. We're told that the probability is even across all these outcomes, 0.25, which is 1/4. And so now, can we talk about if this is a valid probability distribution? It is, because all these events are disjoint from each other, right? If you have 2 kids, only one of these combinations can happen, right? I should add a picture of a baby goat or 2 baby goats. What's the next criteria? Each probability has to be between 0 and 1. Looking at 0.25, 0.25, 0.25, 0.25. Between 0 and 1, that's good. And the probabilities have to total 1, which it does. All right. And so this is a valid probability distribution. Yeah.
Okay, so I understand that this probability equals 1, but if you plot this on that Venn diagram that you are giving us, will the male female not center in the middle when you said this journey doesn't have to.
So in this case, what this would look like in a Venn diagram is not actually that helpful, because it would just be 4 disjoint things, where this would be male, 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 female. Oh, I guess I went rogue here. Female, 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 male. But otherwise, yes. I see, yeah, I see what you mean. But in this case, because we're considering these combinations as one thing, right, then they're just disjoint, hanging out.
If it was just male, if it was just one M, one F, and then you now have MF, then we understand that that is the middle. Like rather than have a double male, if you have like a single male, a single female, and then the third probability is then MF, then we understand that that would center in the middle.
Yes, but because they're disjoint, they can't happen at the same time.
Yeah.
Right. And so, and then you want to be careful that you don't, so if you're considering 1 kid versus 2 kids, those would be 2 separate graphs. A little bit tricky. Any other questions about that one before well, I already scooted on, but. Okay. This one's sneaky, so I'm not going to make you do it, but we'll talk about why it's sneaky. So in a survey, 52% of respondents said that they are Democrats. What's the probability that a randomly selected respondent from the sample is a Republican? Now, I think what we're meant to do is say, oh, well, it must just be the opposite. But then we would be ignoring, remember, there are also independents that run. So it is a 2-party system, but they have, there's a chance that you could have some independent running. And so for that reason, right, it's this one, which I don't like when they do, but they do it a lot. Yeah. And so given this, right, all we can say is, so I would be okay if you said it's less than 0.48, but, oh, sorry, but that doesn't include 0.48. So that's the only reason. And was that your, yeah, that was your comment. You could, but I'm just being picky because this one does not include 0.48. So like I said, I would be fine with you picking that one, but technically because it doesn't include it, we don't know if there are no independents, then it would be 0.48. And so kind of sneaky. So I'd be okay with it. I don't ask questions like that anyways, but just to think about, so we need to be really aware of, okay, just because I know that 52% are Democrats, I can't just lump everyone in as a Republican. I have to think about all the possible outcomes, right? Which brings us to the sample space. So the sample space is the collection of all possible outcomes of a trial. So a trial meaning anytime I flip a coin or I observe 2 kids or 1 kid or thing like that. Draw a card from a deck of cards is going to be considered a trial. And so the sample space is going to be denoted by a capital S. And usually how we list the sample space is a set. And so S is a set. So we use curly brackets. Not so much for you to list the outcomes. You don't have to worry about giving the set, but I do need you to be able to read the set. And so a set would look like this. So a couple has one child or one baby goat. What is the sample space for the gender of this baby goat? I'm going to use curly brackets to denote that this is a set. And I'm going to use male, female. So as long as you're comfortable reading that, you don't have to generate it unless it's on an assignment or something like that. But just as long as you're able to read it, right? The possible outcomes are either male or female. We are considering the binary situation. Now we have 2 baby goats. Just cuter to think about. Well, kids are cute too. Shouldn't say that. But baby goats are extra cute. So now we have 2 of them. What's the sample space for the gender of these 2? We already saw it, right, in the probability distribution. And so we can start by male, male, and then we talked about female, female, and then we distinguish between male, female versus female, male. My left curly bracket always looks pretty reasonable, and then my right curly bracket is just a squiggle that just kind of doesn't stop. And I've written curly brackets for forever now, and I still can't do it, so. Okay. Only one of these things is going to happen, right? But it's the list of all possible outcomes. Complementary events are 2 mutually exclusive events, which we've been calling disjoint, right? So this is a good spot for us to kind of highlight. Okay, you could read that as disjoint if you want, or mutually exclusive, whose probabilities add up to 1. Yeah. And so if you have 1 kid, if we know that it's not a boy, then what is the gender? Because we only have 2 outcomes in this case, we're going to say it's female, right? And so we call these complementary outcomes. Yeah. I have a note to make, but let me see here. So if you have 2 kids, and if we know that they are not both girls, let's see here. Copy this. Because our possible combinations, and we're told that, okay, they're not both girls, then I can remove that female, female, and now I no longer have the sample space of, or the entire sample space, so all possible outcomes. So I'm not going to call it S anymore, but I could call this, I don't know, something else. At least 1M. Something like that. Here's where I wanted to make a note. Because I feel like I didn't get to go on my rant about pie charts. So my rant about pie charts is that pie charts is kind of similar to this, right? If we know that it's not a boy, then you know that it has to be the other thing, right? If I tell you oh, you're going to, let's say, I was gonna say pass a course, but let's say something, the probability that you win the lottery this week is 2%. Wow. What do you know about not winning the lottery? You know, the probability of that is 98%, right? And so you only need to know one of the things in order to know the other thing as well. Okay. And so here I'll make a note about pie charts. And so, because it refers to complementary events. Going back to pie charts, they're really only useful, whoops, getting sloppy here. They're only useful or truly useful if you only have two possible outcomes, right? If we only have two possible outcomes. Right? So our sample space only has two things, right? But then, so that is our sample space only has two things. But then, if you're drawing a pie chart and it looks like this, right? You could communicate that in a better way, right? Let's say this is 70% and this is 30%, whatever it is, right? You could communicate that with one number, right? So because these are complementary events, we can communicate this entire graph with just one number, right? 30%. The probability that you win the lottery this week is 30%. Well, it's still pretty good. It's not. So because these are complementary events, we can communicate the same information with just one number. And so that's kind of tying into our sample space and our complementary events. And also now you're ready. I don't show it right away, but we'll see if it plays. Let's see. I'll try it.
Literally be surrounded by
How do I?
killers? You don't think people in this store do
Pretty good.
marijuana, do you? I mean,
Probably.
wait, how many of them?
Like half.
Wait, half do or half don't?
It's both.
Okay, so
Anyways, do you know how I had to get that? I had to stand in front of my TV. That's how desperate I was to get it out into the world. Superstore is actually riddled with stats jokes. So that's why you think it's so funny. Or I think it's so funny, maybe. But anyways, so kind of an illustration of, okay, pie charts, not that useful. Anyways, I really hate pie charts, if you can't tell. And as a field, statisticians don't like pie charts. Everyone else likes pie charts, but we don't. All right, so we've talked about disjoint outcomes where two things cannot happen at the same time, okay? Now we're gonna move into independence. So two processes are independent if knowing the outcome of one provides no useful information about the outcome of the other. Yeah? And so knowing that I've already flipped heads, right, that tells me nothing about the next outcome. And so what we call that is we call it independence. And let's see here. Okay. I want to add a little bit here. So no useful information. By that we mean about the probability, or maybe I'll do this. Oops. About the outcome or probability. Because technically what the definition says is, okay, knowing that something has happened, that one event has happened, if two things are independent of each other, then it has no impact on the probability of the next event, right? Flipping heads is still 0.5 and flipping tails is still 0.5, right? And so that's independence. So knowing that the first card drawn from a deck is an ace does provide us useful information for finding the probability of drawing an ace in the second draw, right? Without replacement. So here, without replacement. So knowing that there's already one ace out, right, that impacts the probability of another ace being drawn. Right now there's only 3 out of 51 cards, not 52 anymore, right? And so it affects the probability. So it does provide us useful information because the probability changes, right? Without replacement. What about with replacement? You just put it back in, then knowing that I drew an ace already has no effect on the next ace or the probability that I draw another ace, right? Because they're just drawn from the same deck, shuffled, replaced, okay? So that's why it's important to distinguish between without replacement and with replacement. Okay. Good. Okay. Okay. There was a survey that interviewed a random sample of, I guess, 500 North Carolina residents, asking them whether they think widespread gun ownership protects law-abiding citizens from crime or makes society more dangerous. So there is a more elaborate explanation on the next slide, but it kind of dives a little deeper than I want to. So I'm going to explain it just in kind of plain terms, and then we'll just walk through the next slide slowly. Okay, but what's happened here is, okay, all respondents, 58% of them said yes. Okay, and so now if we break it up by race, and we're going to talk about white, black, Hispanic, okay, which I guess is the only ones. Oh well, maybe in North Carolina. Just go with it. So now, ignoring those numbers that are given, if there was no relationship between race and how they felt about gun ownership, what would you expect it to be in each of the races? Roughly 58%, right? Because if everyone is the same and it doesn't matter, then you would expect everyone to be hovering around 58%, right? But then what we see is that 67% of white respondents, 28% of Black respondents, and 64% of Hispanic respondents said yes. So overall, sure, 58. But then within the races, we've got this kind of, I am going to say skewed, but not in the way that we know, right? This uneven distribution. Okay. And so we're going to talk about which of the below is true. So opinion on gun ownership and race ethnicity are most likely, and I'm going to say most likely, I'm just going to give it to you, dependent, right? Because it looks to me, especially with this 28%, right? That's really, really low in comparison to the other groups. 67 and 64, I'd say are relatively similar, right? But not really compared to 58, right? And so we've got this kind of, how can we draw this? Overall, we were at 58%. That's not a very good. No, scratch that. I don't want to do that. I was going to do bars here. 58, 28. Okay, fine, I will. It's kind of a weird way to do it, but. Oh. 67%. 28 is below. And 64 is above, but not as high. I'm just making this up, or this graph up, but just so we can see, right? So, whereas if they were independent, right? If they were independent, we would expect each group to be around 58%. So if they're not independent, then we just say that they are dependent. We're gonna have math ways of figuring this out, right? But it's good to kind of understand the idea, right? If you break it up into groups and they behave differently than the overall, then there is some dependence there, right? Okay. It does jump ahead, but I don't think it's going to hurt to introduce it here. So if the probability that A occurs, given that B is true, we've already seen this given, right? And I said, oh, that's not until the next section, but this, we called it a conditional probability. Isn't until the next section, but doesn't hurt. And so given that B is true, so this vertical bar, you're going to read it as given. So the shorthand would be the probability of A given B. You're going to read this as the probability of A given B. So if we know that B happened, then the probability of A happening is this. If we find that it is just the probability of A, what's that telling us? Well, it didn't care what happened in B, right? And so it's just going to hold steady at the probability of A. So that's the definition of independent events, is when the probability of A given B is just the probability of A. Okay? And this will be on your formula sheet. We're not ready for it yet, but if you have two independent events, then the probability of, no, we're not ready for that. Sorry. Something to look forward to, though. So this is just a mathy way of showing what we talked about before, right? So if we said, okay, if I know the race, then that's not going to affect the overall probability, right? Then they're independent. But we use the flip side of that. And we said, okay, overall, the probability that they think that it protects citizens is 0.58. And then we can break it up here. And because these probabilities, so the probability that they think that it protects citizens given that it was a white respondent was 0.67, right? And so we have this given information, conditional probabilities. We knew how to do that. We just didn't have the formulas for it yet. And we still kind of don't, but a little appetizer for next week. Do I want to skip this one? Maybe. Okay. I do want to highlight just one thing here. So if we have a large difference, okay, two things, between these probabilities, right? They are conditional probabilities that we talked about, but we said, looking back at my makeshift graph here, right? There was a huge difference between 67 and 28. I don't care who you are, that's a big difference, right? I say I don't care who you are because here we might disagree on 67 versus 64, right? Is that a big difference or no, right? But here, the distance between these two down to 28 is going to be considered large no matter what, right? And so then if the observed difference is large, then there's strong evidence that there's a real difference here, right? Not just by chance. Okay? Now here, if the sample is large, then even a small difference could be considered a significant difference or evidence of a real difference, right? And so, so that's going to be key. If you have a large sample and you see and you're looking at 64% versus 67%, then that might be considered a real difference between the two. Right? Whereas if you've collected a small sample, and I think that's what they talk about here, yeah. And so 67% and 64%, under which condition would you be more convinced of a real difference between the proportions, blah, 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 if you have a sample size of 500 versus a sample size of 50,000, right? Going back to the law of large numbers, at 50,000, things should have stabled out a little bit, right? And we have a pretty good representation of what's happening here. So I'll highlight that. Yeah. So if we have a large sample, then even a small difference could be considered. We're calling it a real difference because we haven't done any hypothesis testing yet, but eventually we'll be able to show that there's a significant difference. Okay. I'm going to highlight that it's the product rule for independent events. So if A and B are independent, then you're allowed to say that the probability of A and B is the probability of A times the probability of B. Okay. And this is on your formula sheet. And we already mentioned it, right? And is going to mean multiplication. And so the probability of A and B is just probability of A times the probability of B. Okay? I want you to be really careful though. This is only true for independent events. Okay? Independent events are not necessarily disjoint, right? It just means that knowing the outcome of one has no impact on the probability of another thing, right? Knowing that you got an A in econ doesn't necessarily tell me anything about the probability that you get an A in stats, right? And so they're independent, but they can happen at the same time. And that's where it gets kind of confusing, I guess. But what's nice is you can extend this to any number of events. And if you want them or need them all to happen at the same time, you can multiply them. Yeah? And so, but I can't stress this enough, only for independent events. Yeah? And I'll go back to our formula sheet here and show you. So here, now we have introduced this one. I have this one first on the formula sheet just so you don't get tripped up, but it does include the conditional probabilities, which is in the next section. And so for now, we're just going to focus on the independent probabilities. But what's nice is if I say that A and B are independent and you need to find the overlap, then you can do that now, right, by multiplying the two. What can you do on the flip side? You can prove that two things are independent of each other, right? If you multiply, if you have each of the three probabilities and you prove that P of A times P of B is the probability of A and B, then they are independent. Yeah? But I'm getting ahead of myself. You toss a coin twice. What's the probability of getting two tails in a row? So this is where we're going to start using these slots, I call them, right? So first coin toss has some outcome, second coin toss has some outcome, okay? And I'm going to put what I need the outcome to be, tails, tails. And then somewhere, I'm going to write the probability of each outcome. So probably down here, I'll use a different color, 0.5. Probability of tails, 0.5. Probability of tails is 0.5. And so the probability of these two, probability of tails and tails, right? And maybe I'll use a different color for the tails and tails, right? Two tails in a row, get a tail and another tail. And so the probability of tail is usually how we would denote that, is 0.5 times 0.5, which
So is this like, when you were talking initially, and you had said, like, if you have 11, like, you know, tails in a row, what's the chance the next one's a 0.5? Is it like the overall, if you start with having flipped the coin once, then you do the multiples to find the probability, which will be like 0.25 for 2 flips. But as soon as you land your first flip, your probability is back to 0.5 for the second flip.
yeah, because they're independent. Nice. Yeah, so we can only use this multiplication if they're independent, but in this section, they will be independent, so that's nice. So then, let's go back to what is the probability of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think they had heads in a row. I'm gonna be lazy and just write one head and then fill in the rest. Because what is it? They're all the same, right? So the probability of 10 heads is 0.5 times 0.5 times 0.5 times 0.5. Which is what? 0.5 to the power of 10, which is going to be small, but still possible. 1 over 1024, or the only bummer is it gives me scientific notation. 1, 2, 3, 9, 7, 6, 5, 6, 2, 5. 1, 2, 3, 4. Okay, good. Not 0. Right? You want to be really careful. There is a probability, it's just really small, right? And that's why our gut says, oh, well, that's unlikely to happen, but there is a probability that it can happen. Right? Good. So I use these slots anytime I have independent events, right? Or you can adjust it as long as you're adjusting the probabilities for dependent events, right? Then you can play around with it.
When you write a number like that, are you wanting us to leave it that way, or as the previous fraction, or as the percentage, like moving the decimal?
Because it's a probability, it's safe to just use it, just give it as a probability. And in terms of the exact answer, so the fraction or the decimal, doesn't matter to me, I'll know either way. But I don't want you to do any rounding, right? Whatever you do. Okay. You can write this and then say, or approximately 0. Approximately. Got a big hang up on that. Because this is really large in comparison to 0, right? So lumping it in with 0 doesn't work, but yeah, in exact answer, you could even leave it as 0.5 to the 10, that's fine. It's not about, can you do it on your calculator? But it's nice to see the numbers. So, recent Gallup poll suggests that 25.5% of Texans do not have health insurance as of June 2012, and pretty outdated, I guess. Assuming that the uninsured rate stayed constant, what's the probability that 2 randomly selected Texans are both uninsured? So now randomly selected, hey, that sounds like chapter 1 stuff, and it is. When I say they're randomly selected out of all Texans, okay, then what can I assume? I can assume that they're independent of each other. Okay? So this allows us to assume they are independent. That's good. Because if they're independent, it's easy to find the probability of the first one being uninsured and the second one being uninsured. First one uninsured, second one uninsured. First one uninsured is 0.255 times 0.255, which is, guessed it, 0.255 squared. I got sloppy here. I didn't write out what it was I was interested in first and then the probability underneath, but we are going to be moving towards this. As long as you can keep track of, okay, here I want an uninsured and here I want an uninsured, what we're really interested in is those probabilities, right? And then we're multiplying those. Do the sum of probabilities of two disjoint events always add up to 1? Not really, right? 2 events might be disjoint, but there could be 3 disjoint events in a sample space, right? A, B, C, right? And so knowing that they're disjoint doesn't tell us the total number of events in our sample space. How about complementary events? Well, that by definition has to add to 1, right? You either got an A in the class or you didn't, right? You won the lottery or you didn't. It's binary, right? And so it's either one or the other, which means that the total probability of one of those 2 things happening has to be 1, right? If you take a course, you're either going to get an A or not, right? But one of those 2 things has to happen. If we were to randomly select 5 Texans, what's the probability that at least one is uninsured? Notice that we've got at least one. As soon as we get into kind of more than 2 things, right, it might be nice to list out the sample space. And we need to be really careful because if I have collected 5 Texans, then the number of those that are uninsured includes 0, right? There's some probability that none of them are uninsured, so all of them are insured, right? And so that's going to be really important to remember is that, okay, they're allowed to all be insured, right? And then the other options would be 1 of them is uninsured, 2 of them is uninsured, or are 3 are, 4 are, 5 are. Right? Only 1 of these can happen in 1 sample of 5, right? But these are all the possible outcomes. And so then it becomes a question of, okay, at least 1 person, we're going to translate that into what that means in terms of the sample space. And so at least 1 is 1, 2, 3, 4, or 5. We're just going to lump those into and call it at least 1. So that's kind of a trick that we're going to use quite a bit, is saying, okay, well, maybe it's easier to find the probability that none of them are uninsured and subtract that from 1, right? And so here we can find the probability none are uninsured and subtract that probability from 1. I'll skip ahead. We'll come back to it. We'll use it as review. But we did almost finish, let's see here, the section. So I'll let you work on those assignments that I posted. But we'll use these as review next week. If you have any questions, let me know. Otherwise, see you on Tuesday.